if your textbook really doesn't have a problem on this, there's no excuse. I'm sorry, there just isn't. Do you guys have any questions about homework? I can keep working examples, but yeah.
Do you have an example? I mean, do you have I just gave you the book, I didn't see any, but in the homework questions that aren't from the book, do you have a question with a limit like that? With using series of limits?
I don't have a lot of, there might be.
I didn't see any in the.
No, I don't think I do, but it's not good. I mean, there should be examples of this given. It's an important idea. So again, are there any questions about the homework? So I'll work number 13. We've got 4x over x squared plus 2x minus 3. And we're supposed to find, I think, the Maclaurin series for this. I've got 9.9.
Okay.
Number 13 from 9.9. We're supposed to find the power series expansion about 0 for this function. Now, I don't know about you, but the thought of the brute force approach here, like finding the power series just by successive differentiation and evaluation, no. That would be quite awful. And this is also not, well, look, if I was asked to find the power series about 1, this wouldn't be too bad. Power series about 1, I could do like this. See, this is x minus 1 squared, right? Plus 2, am I right? And so then I could say, well, that's really 4 times x minus 1 plus 4 over 2 plus x minus 1 squared, and et cetera, to find, in terms of the book, c equals 1 expansion. Expansion about c equals 1 you could find from that, just straight geometric. But the book asks us in number 13 to do it for c equals to 0, right? So like, that doesn't help me for c equals 0. What do I need to think about for c equals 0 here? This is what? Does that factor? Oh yeah, is it? Wait, no, does it? All of a sudden I wonder if I copied it down wrong. Plus 2x minus 3. Oh, look! This is a very bad, very bad copying error, because this, yeah. I mean, I can show you how to find the power series for that directly. Maybe that would even be a good exercise, but I think I should put a plus here and a minus here. That's actually what's in the book. See, all of a sudden that becomes reasonable, because that's plus 3 times x minus 1, right? Which means we can do partial fractions on it, and then we can apply the geometric series technique on each piece. All right? So let's go that route. Okay, so this should be equal to a over x plus 3 plus b over x minus 1. So that gives me 4x is equal to a times x minus 1 plus b times x plus 3. And what should I do next? Probably plug in 1 and minus 3, right? X equals to 1 gives me 4 is 4b. b is 1. If I put in x equals to minus 3, I get minus 12 is minus 4a. Apparently a is 3. So the problem we're looking at here, actually, we have f of x is equal to 3 over x plus 3 plus 1 over x minus 1. Now I want to find the Maclaurin expansion for this. Well, that's not bad then, because I can use the geometric series on each piece here, right? Just got to use your imagination a little bit. This is 1/3 of 3 over 1 plus x over 3, right? So I factored a 3 out of the denominator. Of course, those 3's cancel, right? And this one, well, that's just minus 1 over 1 minus x. That's about as simple as you can get for geometric series. And so here you have it. This is the sum, n equals 0 to infinity of minus x over 3 to the n plus, or rather, excuse me, minus the sum n equals 0 to infinity of x to the n. And so that gives me the sum n equals 0 to infinity of minus 1 to the n over 3 to the n minus 1 parentheses x to the n. And there you go. That's the Maclaurin series for this one. You could ask fun questions like, what's the 50th derivative of f? What's the 50th derivative at 0? You know? It's not that complicated. We say the 50th derivative at 0 over 50 factorial has to match the coefficient we just calculated, which would be this. So that would be minus 1 to the 50th over 3 to the 50th. Don't try to put this in your calculator. Minus 1. So therefore, the 50th derivative of this function at 0 is 50 factorial, a rather large number, times 1 over 3 to the 50th power minus 1. So if you just take joy in calculating arbitrarily high derivatives of functions, this is a great method. I don't know why I keep doing this. It's just fun. But what happens if you can't factor? How do you do these? You know, what if it was like one of those things we had to do the arctangent integral for before, remember? Like 1 over an irreducible quadratic? Something like f of x, 1 over, here's my favorite one, x squared plus 4x plus 5, right? I mean, I can find a power series for this centered about 2 without too much difficulty. This is 1 over x plus 2 quantity squared plus 1, right? So if I wanted to find the power series centered around minus 2, rather, I should say, this is the sum, n equals 0 to infinity, minus parentheses x plus 2 squared to the n, which is sum n equals 0 to infinity minus 1 to the n x plus 2 to the 2n. So there's the Taylor series centered at minus 2 without too much work on this one. How would you go about finding the Taylor series centered at 0 for this thing? I'm not sure I know a nice method, honestly. Well, guys, I think we're going to call it a day. If you got questions, bring them back tomorrow.